Hi, this is Jordan. I'm from Zama, and I'm a research engineer in the machine learning team. Today we'll be discussing one of the features that is present in the 1.6 release of concrete-ML. So among those features, we have the ability to now load pre-trained trees directly in concrete-ML from XGBoost or scikit-learn. We have latency improvements, which I'll be discussing later. And we have better deployment, especially for FHE training, and more features to the encrypted data frame. Great. So latency improvements. What we showcase here is that we took the architecture that was once built in the 2021 white paper of Zama, and we reran it using all the advances that were done. And we are going to focus on one, which is the approximation mode. So running this, we actually saw that we had up to 20x speed up in running these NN20. And we have the notebook. You can go and see how you actually can do this. And the second part is ResNet 18, where we took a pre-trained model from TorchHub and just pass it through the PyTorch function that I'm going to explain right after. So yeah, this function, I really wanted to emphasize on it because I think you can convert any kind of model that you build in Torch directly to the FHE realm and run the model on encrypted data, right? So here are a few things that we're going to import, and we are going to define a P error. So basically, machine learning models are kind of robust to high P error. So this P error is the probability of 1 in the quantized world. So I'm not going to explain this in too much detail, but you can know that you can actually increase that and check the accuracy. So we are defining a very simple neural net. We initialize it. Something that is very important is representative data. So here it's just random for the demonstration, but what you can do is take a few examples from your trading set just to show how the boundaries within your network are going to be in FHE. And we are going to present two different modes, the rounding in the exact mode and the rounding in the approx mode. So long story short, what the rounding does is that it takes any kind of intermediate value from your neural net and it rounds it down to a specific number of bits. So here it's going to be 6. What we realize is that you don't really need the full precision on every single intermediate value, like the result of a matrix multiplication. But what you do need is the most significant bits. And keeping a few of them improves a lot the FH execution while not impacting the accuracy, right? And now we're going to call this compile torch model. We throw in the model, representative data, we select the parameters precision and input precision, and throw in the rounding and P error method, right? So we're going to compute this, and what we are going to do next is check the timings for the first method, which is the exact one. So here it compiled both circuits. Now we are running the exact method, and we're going to check the results. So here we encrypt, we run the model in FHE, and we decrypt and go back to the floating points. And we see the results here. So it actually ran before. It's going to take around 17 to 18 seconds, hopefully. Yeah, 22 seconds here. And now we are running the approx mode. It's 2.6 seconds. And we can run as well the torch model to compare all the results. And we see that everything is fairly close and that this would work for maintaining the accuracy pretty high. And that's basically it. You can start building with this function and with the approximate mode and see what you get. Thanks a lot for your attention.